Thank you very much. And yeah, thanks for that I can tell about my work here. I was kind of happy to hear about this community with shared interests. So yeah, I'll talk about perturbations of Minkowski spacetime. Sorry, I have to. Yeah, no, I'll talk about perturbations of Minkowski spacetime in general relativity, and as is appropriate for this seminar series, I guess, we will focus in particular on the behavior of the null asymptotics. So roughly, the goal will be to identify sufficient conditions on the initial data such that the corresponding perturbations admit a smooth or sufficiently regular conformal compactification at null infinity and time-like infinity. So let me start by recalling the conformal compactification of Minkowski spacetime itself. This will also allow me to introduce some notations. So for this, we take the Einstein cylinder, which is R times the 3-sphere, together with the standard Lorentzian metric, the standard Lorentzian cylinder metric. Tau here is the time coordinate on R, and in the picture, this goes up. The GS3 is the standard round metric on the 3-sphere. And note that this 3-sphere is here drawn as an S1. Now, Minkowski spacetime is conformally isometric to this blue patch here on the cylinder. I'll denote this by D for Minkowski diamond. So here's spacelike infinity, future time-like infinity, past time-like infinity, and the green lines indicate future null infinity, so scry plus, and past null infinity, scry minus. Now it will actually be useful to have a definition of this diamond. So it's given by all points tau and xi on the cylinder, such that tau is strictly between pi and minus pi. So here's tau equal 0, tau equals pi and minus pi. And further, the function cosine tau minus xi4 has to be strictly positive. So you see, I view here this vector xi, or this point xi on the 3-sphere, as a vector with 4 components, xi1 up to xi4, and with length 1. And this xi4 is the last component of this vector xi. Now let's give this function here a name. Let's call this h. Now this h is the conformal factor of Minkowski spacetime. It vanishes first order along null infinity, so scry plus and minus, and it vanishes second order at spacelike and time-like infinity. So more concretely, the Minkowski metric on the diamond is given by this conformal rescaling 1 over h squared of the cylinder metric. So this patch D on the cylinder together with this metric is a copy of Minkowski space. Now in particular, we can choose coordinates x, which go from x0 to x3, which identify this diamond with R4. And with respect to these coordinates, the Minkowski metric takes the standard form. Now, in this talk, we want to construct perturbations of Minkowski spacetime. So we want to find smooth Lorentzian metrics G on the Minkowski diamond, which are close to the Minkowski metric, and which solve the vacuum Einstein equations. Now, from the work of Helmut Friedrich, who is, I think, also in the audience, we know that also certain perturbations of Minkowski spacetime admit a smooth conformal compactification, namely perturbations that are identical to a Kerr black hole spacetime in such a neighborhood of spacelike infinity. Now, these perturbations can be constructed as follows. We first fix a initial hypersurface. Say this one, I'll always take tau equals 0 to be the initial hypersurface. And we take initial data, so solutions of the constraints, which are identical to Kerr near in this neighborhood here of spacelike infinity. So these are the solutions of the constraints, which were first constructed by Corvino and Schön. Now, by finite speed of propagation, we then know that the corresponding Ritchie-Flat metric is identical to Kerr in this whole four-dimensional neighborhood of spacelike infinity. So the remaining task is to construct the metric in this remaining yellow region. So this one here and also back here. Note that this yellow region is compact and it does not touch spacelike infinity. Now, in this region, one can conveniently construct the metric using Friedrich's conformal field equations. So the conformal field equations are a formulation of the vacuum Einstein equations, which remains regular, including at null infinity. So with these equations, one can essentially reduce the problem of constructing the metric to solving a hyperbolic PDE with small data on this yellow compact domain. And in particular, one then immediately obtains that the metric indeed admits a smooth conformal compactification at null and time-like infinity. Now, requiring that the initial data be identical to Kerr near spacelike infinity is somewhat restrictive. And there are other works, for example, due to Christodoulou-Kleinerman, Lindblad-Rodnianski, Hintzwashi, Bieri, and many others, that work with more general different types of asymptotically flat initial data. But under these more general assumptions, the metrics are not shown to admit the smooth conformal compactification. So the situation that we're interested in this talk is more closely related to this Corvino-Schön-Friedrich situation. However, instead of taking data which is exact Kerr near spacelike infinity, we want to take data which only asymptotes to Kerr towards spacelike infinity, either at a rapid rate or more generally at an inverse polynomial rate. Inverse polynomial with respect to these x coordinates. We then want to construct the corresponding solutions of the Einstein equations, and we then want to understand the regularity properties of the solutions at null and time-like infinity. So roughly, the theorem that I'll state at the end of the talk will say that the faster the initial data decays to Kerr towards spacelike infinity, the more regular the solution is at null and time-like infinity. So decay to Kerr towards spacelike infinity implies regularity of the conformal compactification. Now for this, we have to solve kind of two tasks. We first actually have to construct solutions of the constraints. Now with this more general asymptotics and given solutions of the constraints, we then have to address the hyperbolic problem, which is then not a hyperbolic problem on a compact domain anymore. Now, in this talk, I will not discuss the constraints. So the theorem that I'll state will be conditional on the existence of solutions of the constraints with certain asymptotics at infinity. But in a paper from a while ago, I wrote down a solution operator for the linearized constraints about Minkowski with optimal asymptotics at infinity. And with this operator, one can actually write down the appropriate solutions of the constraints. So in the remainder, let me focus purely on the hyperbolic problem. Now, we want to understand null asymptotics, and therefore we want to use a formulation of the Einstein equations in which these asymptotics are as simple as possible. So we will not use Ricci equals 0, but an equivalent reformulation of it. Now, this reformulation will be essentially a repackaging of the Newman-Penrose orthonormal frame formalism. However, the way in which I will write it down will make the regularity properties at infinity more tractable. Now, also, this will be related to the conformal field equations. However, it's not the same, so one important difference will be that in this formulation, the conformal factor will not be used as an unknown. So to tell you what this formulation is, I have to tell you what the unknowns are. And then I'll have to tell you what the equations are. So we are in an orthonormal frame formulation, so the unknowns are an orthonormal frame for a metric, then the coefficients of the Levi-Civita connection relative to the orthonormal frame, and then the coefficients of the Weil curvature also relative to the frame. Now, the frame and connection will be elements in the following space. Omega 1 here are the smooth differential one forms on the Minkowski diamond. And given these coordinates x, a basis of this space is given by the differentials dx0 up to dx3. So elements in omega 1 of d are linear combinations of these differentials here, where the coefficients are smooth functions on the diamond. Now, K here is a 10-dimensional vector space, and concretely it is given by the killing fields for the Minkowski metric. So a basis of this space is given by the translations T mu and the boosts B mu nu, which is x mu partial x nu minus x nu partial x mu. I'm raising indices with the Minkowski metric, and note that these boosts are antisymmetric. So up to sign, we really have here 10 distinct basis elements. Now, it is important that this is really a 10-dimensional vector space, so we cannot multiply these basis elements by functions, only by real numbers. Now, there will be two properties of these killing fields which will become important. The first is that they are actually smooth vector fields on the whole Einstein cylinder. So, for example, it is easy to check that these 10 vector fields here indeed extend smoothly across the Minkowski diamond. Now, the second property is that they are also tangential to the boundary of the diamond. So, for example, if you take the flow of such a vector field, then the Minkowski diamond, under this flow, it is mapped back to itself. So let's now go to the Weil curvature. The Weil curvature is an element in a space which I denote by I2 of D. And this is a rank 10 submodule of the differential 2 forms on the diamond tensored with the differential 2 forms on the diamond. So this has rank 10, which is the right number for a space of Weyl curvatures. So note that elements in here are just tensors with 4 indices, W, A, B, C, D. And where the coefficients are antisymmetric in AB and in CD. Now, I2 is just given by those tensors which have all Weyl symmetries. So where the trace over A and C vanishes and the sum over cyclic permutations of B, C, D vanishes. Now, before I go to the equations, I want to make precise how an element in here, in this space, defines an orthonormal frame and hence a metric. So we take an element U0 in our space of differential one forms on the diamond, tensored with the killing fields. And our goal is to write down the associated metric, which will be a Lorentzian metric on the Minkowski diamond. Now, for this, we expand our U0 in a basis, namely using the basis which I just wrote down up here. So we have some coefficient functions times dx mu translation nu, and then some other coefficient functions times dx mu, and then beta nu alpha. Oh, sorry, I should write this nicer. So this was the nu alpha boost. Now, actually, I don't want to use exactly this basis, but it is more convenient to subtract certain translations from these boost terms, namely these ones here. So this is more convenient because then the coefficient functions have a clearer interpretation. So let's give the coefficients names. Here is f, and here is -1/2 eta alpha beta gamma beta mu nu. Now these coefficients give the orthonormal frame and hence the metric, and the gammas give the connection. Now, more precisely, the inverse metric associated to the U0 is given by this expression. We have eta mu nu, and then delta mu alpha. This delta here is the Kronecker delta, plus f mu alpha, and then the same with nu and beta, and then times dx alpha tensored with dx or partial x beta. Now, this expression here is really the inverse of a Lorentzian metric on the Minkowski diamond if this matrix, so identity matrix plus f, is invertible at every point on the diamond. So let's add this assumption here. So I want identity plus f to be invertible. Note that then this formula also tells us that, that these 4 vector fields here, so we sum over alpha and mu goes from 0 to 3, so we have 4 vector fields here. These 4 vector fields are an orthonormal frame for the metric G. So that's our orthonormal frame. And actually these gammas down here, these gammas here are then the connection coefficients of the Levi-Civita connection with respect to that orthonormal frame. Now, in order to understand the regularity properties of this metric at null infinity, it is useful to rewrite this formula here in an equivalent but slightly less coordinate-dependent way. Now, for this, we write the U0 as a sum of such product elements. Omega 1 up to omega 10 are 1 forms, so elements in omega 1 on the diamond, and K1 up to K10 are a basis of the killing fields. So for example, one can use the basis here, but it actually doesn't depend on which basis like one can choose any basis. Now this expression here defines a map FU0 from vector fields to vector fields. Namely, given a vector field, let's call it X, we can insert it into omega I. Now this is a function. Then we can multiply with Ki, so with the killing field Ki. This is now a vector field, and now we sum over these 10 vector fields. So the input is a vector field as well as the output. Now actually this formula here for the F, or this definition, is just a kind of a coordinate independent way of extracting this matrix F mu nu. Namely, if we apply this F U0 to partial X mu, then it's given by F mu nu partial X nu. So we get precisely these F mu nu's back, which we need to define the metric. So in particular, our inverse metric here is equivalently given by this expression. We take the second tensor power of identity plus F, and we apply it to the inverse Minkowski metric. So note that the inverse Minkowski metric is a vector field times a vector field. So it's dx times dx, well, a sum over such elements. And now this expression here just means that we apply identity plus F to each of the two factors. Now recall that we have this formula here for our Minkowski metric. Now therefore I can replace the inverse Minkowski metric here by the inverse cylinder metric if I also do a conformal rescaling on the left-hand side. Now the inverse cylinder metric is smooth and regular on the whole cylinder. Therefore, this expression tells us that if U0 is regular, including at null infinity, then this conformally rescaled metric is regular at null infinity. Or more precisely, if we know that U0 is regular at null infinity, then this means that these one forms, omega I, are regular at null infinity. Then F is regular. And then from this formula, we obtain that h squared g, so the conformally rescaled metric is regular. So let me write this down. If we know that U0 extends, say, with L derivatives to the boundary of the diamond, not space-like infinity, then also the conformally rescaled metric h squared g extends with L derivatives to the boundary. And again, this h here is really the explicit conformal factor cosine tau minus xi4. So the same conformal factor as one has for the Minkowski metric. Now there's a second conclusion that we get, which relies on the killing fields being tangential to the boundary. Namely, the conformal factor h solves the iconal equation on the boundary of the Minkowski diamond. Now, therefore, our metric G as a metric on the Minkowski diamond is null geodesically complete. So if we take any future directed null geodesic relative to the perturbed metric G, then this will hit the boundary of the Minkowski diamond at infinite affine parameter. Now, more precisely, this null geodesic will hit scribe plus, so the null infinity locus of Minkowski space. Now, therefore, this scribe plus here, so the green locus, is null infinity not only for the Minkowski metric, but also for the perturbed metric G. Now, this fact is important because it essentially allows us to construct solutions of the Einstein equations on the fixed background manifold given by the Minkowski diamond. Now, note that we have not solved an equation yet. So this property is just essentially encoded in the degeneracy properties of the killing fields at the boundary of the diamond. So this kind of using this space here might look a bit funny, but it kind of encodes certain properties of the metric at the boundary. So the next I will do is I will explain the equations. Now, are there any questions about like what we have so far? Okay, so you can also interrupt me at any time. Good, so let's now see how the Einstein equations look in this formulation of GR. So we are in an orthonormal frame formulation, therefore the equations are first order and quadratically nonlinear. So the D here is a linear first order differential operator. And this operator describes the Minkowski background. The bracket here is also a first order differential operator, but this one is bilinear. Physically, this operator describes the nonlinear interaction of gravitational waves. And also, this is the part which contains the quasi-linearity of GR. Now, the U is the unknown in this equation. So it is an element in our space of differential one forms times killing fields, and it also has Weyl curvature. Now, actually, let me give this space here a name. I'll call this G1. So, and maybe the U0 that we discussed on the left-hand side would be the component of U that lives in this piece here. So I will not give you full definitions of these operators here, but I'll just give some indications. So let's start with the D here. This D takes the U in G1 and it maps it to the following space, the differential two forms on the diamond tensored with the killing fields. And it also has values in another space, which I call I3. Now recall that the I2 was a subspace of omega 2 times omega 2, defined by certain symmetry and trace-free conditions. Now the I3 is a subspace of omega 3 times omega 2, also defined by certain symmetry and trace-free conditions. So let's call this space G2. So the D takes U in G1 and it maps it to G2. Now it has three parts. one maps like this is another part, and the third is like this. Now for concreteness, I will only explain how this arrow here is given, this part, which takes the U0 and maps it to a differential two-form times killing fields. So the U0 is a sum of terms omega times k, where omega is a one-form and k a killing field. Now applying d to such a product element is just given by applying the de Rham differential to the form omega. So we have the de Rham differential on omega. This is actually a two-form, and then we tensor with k. So let's make this a bit more concrete. For example, if we apply the d to some coefficient function times a basis element, say the basis element dx0 times the 2-3 rotation, and then this is given by applying de Rham on f dx0, which is partial x mu f dx mu wedge dx0 times b2-3. So you see that the coefficient function f is just differentiated with respect to the coordinates x mu. Now let's go to the bracket. This also takes values in this space G2. But again, for concreteness, I'll only explain how the bracket of the U0 part with itself is given. Now, to specify this, I have to tell you how the bracket is defined on two distinct product elements. So here, omega and omega prime are both one forms, and k and k prime are killing fields. Now, this is a sum of three terms. The first term is C infinity bilinear, so it does not take derivatives. And this bracket here is the Lie bracket in the Lie algebra of killing fields. Now in the second term, we actually take derivatives, namely we have the Lie derivative with respect to k of omega prime, and then tensor with k prime, and the third term just makes the whole thing symmetric. So let's again see how this looks for basis elements. Let's take, for example, dx0 times translation 0, and then a coefficient function dx1 times, say, the 0-3 boost. So in the first term here, we just wedge these forms. So this gives f dx0 wedge dx1. And then we take the Lie bracket of T0 with the 0-3 boost. So this Lie bracket here. Now this is equal to the T3, so the translation in the 3 direction. So here we tensor with T3. Now in this second term, we have dx0. And then we have the Lie derivative with respect to the T0 of f dx1, and then tensor with the boost. Now what's this Lie derivative here? This is partial x0 of the coefficient function times dx1. And now we have this third term where we take the Lie derivative with respect to b03 of dx0. Yes, and then we have f dx1 and tensor with t0. Now this Lie derivative here is the dx3 differential. So that's all the terms that we have. Now let's again track the coefficient function. In the first term and the third term, it appears C infinity linearly, so undifferentiated. In the second term, it is differentiated with respect to x0. So let's now go back to our equation here. this also takes values in this space G2. Roughly, the components of the equation that lie in this space, so in the first component, are the conditions that the connection is torsion-free and that the Riemann curvature is equal to the Weil curvature. The components in here are the equations of motion for the Weil curvature. Now, this equation is equivalent to the vacuum Einstein equations in the following sense. I'm now going back to the left-hand side here. So if in our, like here, if we not only take a orthonormal frame and connection U0, but we take also Weil curvature, and if we assume that our U is that this solves our quadratically nonlinear equation, then the metric that I wrote down here is Ricci flat. Now, I mainly told you how in this box one gets from left to right. However, one can also go in from right to left, so in the other direction. Namely, given a Ricci flat metric, one has to choose an orthonormal frame, and then one can write down the corresponding solution of this equation. Essentially, the orthonormal frame and connection part, so the part in here, is just given by using this formula here, and the part in I2 is just the Weil curvature. And also, this is then a one-to-one correspondence if one takes into account the respective gauge groups. So let me add here that this is now our full space of unknowns, which we called G1. Now, let me just mention that these spaces here, the G1 and the G2, and these differential operator, the D and the bracket, are actually parts of a larger structure, namely of the structure of a differential graded Lie algebra. So what this means is just that this D and this bracket satisfy various algebraic identities. I'm also saying this because it motivates the notation that I've used here. So for example, the D is then a differential, so that's why it's called D. So for example, it squares to 0. But that's kind of a side remark. Now, I still have to tell you in what sense this reformulation of the Einstein equations is regular at null infinity. Now, so far, I have defined these spaces and the differential operators on the Minkowski diamond. However, the definitions also make sense on the Einstein cylinder. So let's, for example, look at this G1 space here. So I should have written that this was omega 1 of D. But instead, so here we had differential 1 forms on the diamond. However, instead of taking differential 1 forms on the diamond, we can just take differential 1 forms on the Einstein cylinder. So instead of D, we can take R times S3. And similarly, for the Weil curvature, instead of taking Weil curvatures on the diamond, we can take Weil curvatures on R times S3. So we get a space on R times S3, so on the cylinder. And the same for G2. Now, furthermore, these definitions here define the differential and the bracket also on the whole cylinder. So these formulas just make sense verbatim on the whole Einstein cylinder. Now, for the bracket, this actually uses now the fact that the killing fields, which appear in the Lie derivatives here, that they are smooth vector fields on the whole cylinder. So altogether, we obtain that this D and the bracket are smooth differential operators on the cylinder. Now, furthermore, our Einstein equations here are regular at the boundary of the Minkowski diamond, in the sense that there are gauge fixing conditions such that these Einstein equations are quasi-linear symmetric hyperbolic, including at the boundary of the diamond. So the emphasis is here really that this works also at the boundary of the diamond. So the principal part does not degenerate there. Now, this is very important because this is the reason why we can actually construct solutions U of the Einstein equations, which are regular at null infinity. So which actually satisfy this property here. And therefore, by this kind of green box here, they will then give rise to metrics which have a regular conformal compactification. Now let me relate this a bit to the conformal field equations of Helmut Friedrich. So also the conformal field equations are quasi-linear symmetric hyperbolic, including at the boundary of the physical domain. So this property here is essentially the same. What is different is the fact that we had here. So in the formulation that I've just explained, null infinity is a fixed locus. So the null infinity locus for Minkowski space, for the Minkowski metric, is also the null infinity locus for the perturbed metric G. In the conformal field equations, this is different. Namely, there the null infinity locus depends on the solution. So if in the conformal field equations one starts with the Minkowski metric and perturbs a little bit, then the null infinity locus will move around. This is essentially because the conformal factor is there used as an unknown. So this is all I was going to say about this equivalent reformulation of the Einstein equations. Are there any questions?
I was wondering, could you say a little bit more about the gauge fixing that you mentioned there? So you said, that there exist gauges in which everything is still regular, but could you say a few more details about that? Thanks.
Yes. So there's the gauge fixing has two parts basically. One has to choose a gauge for the unknown, so for the U, and then one also has to choose equations. So one has to choose kind of a square subsystem of this whole PDE. And maybe let me explain how one chooses a gauge for the unknown U. So it's kind of like a Coulomb gauge condition. So the U is, I mean, I will say a bit more at the end about this, but so the gauge condition is that I define a subspace of this G1. So let me call this G gauge of this space of unknowns. And this is like in the Weil curvature, it's the same. There's no gauge condition. So it's something plus the whole space for the Weil curvature. And now the place where we do impose a gauge is the differential one forms. And essentially what one does is we fix one has to fix a time-like vector field. And kind of the important thing is that one chooses a time-like vector field that kind of goes through null infinity. Like, for example, one cannot choose partial x0 because this gets tangential to null infinity. So this would not be a good vector field. But for example, the partial tau vector field would be good. And this gives me a 1+3 splitting of these differential one forms. So it's, say, if I choose the partial tau, it would give me d tau and then three other one forms that are orthogonal to it. And now the gauge condition that I want here is I take the subspace of the differential one forms, which does not have a d tau, but only kind of the spatial pieces.
Okay, so that's the sense in which it's like Coulomb.
Yes, exactly.
Yeah, thank you.
And then, so this kind of chooses the space for the unknowns, and then this is like this equation will then not be a square system, but the equations then kind of split into two types of equations. One's like there's a square system, which is symmetric hyperbolic, and the remaining equations are the constraints, which then again solve a symmetric hyperbolic system, so they propagate. And kind of the way in which one identifies the square subsystem is by kind of one can generalize this subspace here. Like similarly, one can define a subspace of this space for the equation, so of the G2. It's essentially in the parts with the forms, which is then omega 2. It's kind of again saying there's no d tau pieces, and there's like a similar condition then for the space I3 kind of for the Weyl curvature part.
Thank you.
Good. Okay. I'll say something about this like at the end, I think, as well. Any other questions?
If I may, I understand this is for perturbations, and I'm wondering, where does this break? How do you see where it breaks, if it's strongly nonlinear all the way out and so
on? I think there's kind of two things. One thing is that if one only looks at the interior of the Minkowski diamond, then it's just a one-to-one correspondence. So then, like when this 1 plus f here is like as long as this 1 plus f is invertible, such an element in like a solution of these equations give a Ricci flat metric. So that's kind of the only condition which has to hold. But actually here, yeah, maybe I should have also said this. Like in order for 1 plus f to be invertible, like one sufficient condition for it is that the u is small. So because when u is small, then the f is small and then it's invertible. So it's kind of, yeah, that's like one point where it can break down. If one has a solution of this equation where this is not invertible anymore, which happens in particular when u is big, then it breaks down. So yeah, for example, also you see that this equation has the trivial solution u equals 0, and this gives the Minkowski metric. So u equals 0 gives Minkowski, and so yeah, it breaks down as soon, like if you have, so u equals 0 is Minkowski. Like here we're interested in perturbations of Minkowski, so the u will be small and then the f will be invertible. But yeah, it breaks down when this 1 plus f is not invertible anymore. But this does not like this. It can still be invertible if one is quite far away from Minkowski. So it's like in the interior of the diamond, it's really just an equivalent way of stating the Einstein equations. Like the place where it's kind of the story that breaks down if one is not close to Minkowski is like all the regularity, the whole regularity analysis at null infinity. Like this only makes sense for small u's. Does this somehow answer the question?
Yes, thank you. That's what
okay. Okay. So yeah, I think like if there's also, I should maybe, or kind of this way here of like this funny way of writing the Einstein equations. So this was, which kind of involves this differential graded Lie algebra picture. This was first introduced by Eugene Trubowitz and Michael Reiter. And they gave a version of this story that does not involve any background. So it is just really an equivalent reformulation of Ricci equals 0. And what I'm doing here, if I'm restricting to the interior of the diamond, it is like my structure is isomorphic to what they have. It's not like an obvious isomorphism, but it is isomorphic. So in this sense, like one can pass to this more background independent framework. But as soon as I want to understand regularity properties of my metric at the boundary, I have to be small. And then like kind of this boundary behavior is also not contained in this more background independent story that they had. So yeah. Any other questions? Okay, so I'll now go towards the theorem. But before I state the theorem, let me kind of recall what we actually want to do. So I've here drawn now just the Minkowski diamond without the cylinder, but recall that these 2 points are the same. Now we want to take initial data on this initial hypersurface here, which decays to Kerr towards spacelike infinity. We then want to construct the corresponding solutions of the Einstein equations and understand the regularity properties at null and time-like infinity. Now, actually, I will only construct solutions for positive time, so in this upper piece of the diamond. So not here. But this is not a restriction of generality because one can run the construction to the future and to the past, and they fit together smoothly along the initial hypersurface. Now, before I can state the theorem, I have to tell you a little bit about Kerr. Now, we'll only be interested in Kerr near spacelike infinity. So in such a neighborhood here, let's call this delta. And this one here is the same neighborhood. Now, via our one-to-one correspondence between Ricci flat metrics and solutions of the Einstein equations in this form, the Kerr family of metrics defines a family of elements depending on mass and angular momentum in our space of unknowns, and they're defined on delta. And they solve the vacuum Einstein equations. So concretely, to write down these elements, one takes the Kerr metric, chooses an orthonormal frame for the Kerr metric, and then these elements K in a basis, they're just given by the components of the orthonormal frame, of the Levi-Civita connection, and the Weyl curvature. Now, in a suitable gauge, these elements K here are smooth, including along null infinity. At spacelike infinity, they're mildly singular. So they're smooth, including at or on the closure of delta, which includes null infinity, but not spacelike infinity. Now, actually, to get this smoothness at null infinity, it is really convenient to use the Kerr-Schild formulation of Kerr. That's kind of just a remark. Like I tried this with Euler-Lindquist, and it was much more complicated, and somehow Kerr-Schild really fits in well. Now, at spacelike infinity, these elements are mildly singular, and therefore we will need an estimate there. So recall that on the diamond, let me actually call this future diamond D+. So also on this D+, we have coordinates x. Now, these x coordinates are singular at the boundary of the diamond, so in particular at spacelike infinity. Therefore, near spacelike infinity, we use different coordinates, which I call y, and which are related to the x coordinates via Kelvin inversion. So these are now regular coordinates in a whole neighborhood of spacelike infinity, and spacelike infinity is the origin in these coordinates. Now we have the following estimate for Kerr. So this estimate holds on delta. It holds for all non-negative integers L, and it holds for all sufficiently small m and a. And in particular, note that the constant here of this estimate is independent of the mass and angular momentum. Now, the notation here means that we differentiate Kerr L times with respect to the vector fields norm of y, partial y0, partial y1, 2, and 3. Now, in particular, these vector fields here, they are homogeneous. So by this, I mean that they are invariant under scaling y by a positive number lambda. And note that this scaling scales about spacelike infinity. Sorry. Now this estimate here holds component-wise, so for each component of Kerr, where we use a homogeneous basis. So by this, I mean the following. This scaling here, this induces an action on our spaces G1 for the unknowns and G2 for the equations. This essentially just acts by pullback. And what is important is that this action commutes with the D and the bracket. So it is a symmetry of our Einstein equations. Now, by a homogeneous basis, I mean a basis which is invariant under this action. So if one takes a basis element and essentially pulls it back along this scaling, one gets back the same basis element. Now, the advantage of using such a basis is that you see that here I've written down one estimate which holds for each component of K. Now, if one does not use such a homogeneous basis, then I would have to write down different estimates for different components of K. So in such a homogeneous basis, all the components behave the same. If one doesn't use a homogeneous spaces, then different components can behave differently, which makes just the estimates more complicated. So this scaling here is actually kind of an organizing principle for all the estimates that we'll do. So we now have everything that we need for the theorem. So let's look at the theorem. This theorem is, it's in this paper here, in this preprint, and I'll actually give you a simplified version of the theorem. In the sense that all the estimates that you see here are pointwise estimates. So the main theorem in the paper uses Sobolev norms, and therefore it is a bit less, like the main theorem is a bit less lossy than the one that I'm presenting here. But actually this one is also written down in the paper because it is a bit easier to understand, I think. So the theorem has three parts. Here's inputs, so input parameters, here's assumptions, and then we have conclusions. So let's start at the beginning. N is an integer which is larger than 11, and delta is a neighborhood of space like infinity, like the one that we had here. Now, given such an n and a delta, the theorem produces a number epsilon 0, and the assumptions and conclusions of the theorem will depend on a small parameter epsilon, which can be at most epsilon 0. Now, K is an element in our space of unknowns. It is smooth, it is defined on delta. It is smooth, including at null infinity, but it doesn't have to be smooth at spacelike infinity. So you should think that K is Kerr. In particular, Kerr will satisfy all the assumptions. However, it's not logically required to be Kerr. Now, U bar is initial data. So it is a section of our space of unknowns on the initial hypersurface. So we assume that K solves the Einstein equations, and we assume that the data solves the constraints. Now, strictly speaking, I have not told you how the constraint equations look in this formulation of GR, but they are some partial differential equations on the initial hypersurface, which are the necessary and sufficient conditions for local solvability of the Einstein equations. Now, there are three smallness assumptions. The first one is on K and its first n homogeneous derivatives. Now, this has to hold on delta, so it is a smallness condition near spacelike infinity. Now, note that by the estimate here for Kerr, this assumption is satisfiable for Kerr if we make the mass sufficiently small, namely smaller than the epsilon. Now, the second assumption is the key assumption. This is an assumption on the initial data U bar, and it is an assumption near spacelike infinity. So this estimate has to hold here and here. So concretely on the intersection of delta with the initial hypersurface. So note that this assumption now says that the initial data U bar and its first n homogeneous derivatives have to decay to the initial data of Kerr sufficiently fast, namely at a rate determined by n. Now note that y to the n plus 2 in x coordinates, this is 1 over x to the n plus 2. So this is inverse polynomial decay in x coordinates. Now also, this is now a non-trivial, or it is a non-trivial assumption that there are actually solutions of the constraints which have such asymptotics. However, again, like with this solution operator for the linearized constraints that I mentioned at the beginning, one can actually write down such solutions. Now, these first two smallest assumptions, they tell us in particular that the initial data U bar is small near spacelike infinity. Now, the third assumption also requires that it is small in the remaining part. So let's call this part B. So this estimate has to hold on B. Under these assumptions, the theorem produces a solution U of the vacuum Einstein equations with initial data given by U bar. And the associated frame 1 plus F is invertible. And recall that this was the assumptions that we needed in order that associated to U, we really have a Lorentzian metric on the diamond. So our metric G really exists. And then our quadratically nonlinear equations here tell us that this G is Ricci flat. So we now know that associated to this solution U here is really a Ricci flat Lorentzian metric on the Minkowski diamond. Now, the second conclusion tells us that our solution U is regular, including at null infinity, namely with n minus 6 derivatives. And by our discussion on the second page that we had, we then know that our metric G has a regular conformal compactification at null infinity, also with n minus 6 derivatives. So the conformally rescaled metric H squared G, where H was cosine tau minus psi 4, also has n minus 6 derivatives at the boundary. Now, this estimate here tells us that U, the solution U, is small away from spacelike infinity. And this estimate here, which again holds on delta, so near spacelike infinity, it tells us that the solution U, now kind of the four-dimensional section, decays to Kerr at a rate again determined by n. So the assumption here kind of was a similar estimate, but for the initial data. So this conclusion tells you that kind of this decay of the initial data is inherited by the solution. Now let me illustrate what we have so far in kind of a concrete case. So let's say n is, for example, equal to 11. So what does the theorem tell us then? This key assumption then requires that the initial data U bar and the first 11 homogeneous derivatives so these first 11 homogeneous derivatives have to decay to Kerr like O of y to the n plus 2, so to the 13. Under this assumption, our conclusion here tells us that the solution then has n minus 6, so 5 derivatives at null and time like infinity. Now, the third conclusion tells us that if we actually know that the first 12 derivatives of the initial data decay to Kerr one order faster, namely like y to the 14. So note that we have one more derivative, but all of the derivatives have to decay one order faster. Then we get 6 derivatives at null and time like infinity. And similarly, if we know that the first 13 homogeneous derivatives of the initial data decay to Kerr like O of y to the 15, then we get 7 derivatives at null and time like infinity, and so on. So faster decay of the initial data to Kerr implies higher regularity of the solution at null and time like infinity. which is kind of what we had set out for. So in this last item here, this is just spelled out again for general n and for a general number of derivatives. Now, one important thing is that this higher regularity statement here, this does not involve any additional smallness assumptions. So in particular, we get the following corollary. If we actually know that our initial data decays to the data of Kerr rapidly, or in other words, if this difference here is Schwartz, then the solution U is smooth, including at the boundary of the diamond, not space-like infinity. And hence the associated metric G has a smooth conformal compactification. So I realize I'm a bit over time. Do I still have like 3 minutes?
Yes, I think
Okay.
people can leave when they want to, and it's recorded.
Okay, good.
Thank you.
So I'll say a couple, that's the theorem, and I'll say a couple of words about the proof. Very briefly. So the main task is to construct a solution U near space-like infinity. So on our set delta. Now on delta, we write U as a sum of two parts, V and C. The V is K plus an extension of the initial data from time 0 to positive time. And you should think of this as K plus small. So this part here, the second piece, is smaller than K, essentially by our key assumption. The C is the new unknown then, and this solves trivial initial data. Now we rewrite our Einstein equations for U, so this one here, as an equation for C, which gives this equation here. This just uses linearity of the differential and bilinearity of the bracket. So here we have a linear term applied to the unknown C, and recall that the D here describes the Minkowski background. The V here involves Kerr and is hence singular at space-like infinity. Then here's a quadratic term, which is very small if C is small, but it also contains the quasi-linearity. And then here's the inhomogeneity. Now in this homogeneity, note that if we replace the V by Kerr, then this term vanishes because Kerr solves the Einstein equations. So here in this inhomogeneity, actually this extension of the initial data dominates. Now, in order to get a symmetric hyperbolic system, we impose gauge fixing conditions on C. So when David asked before, I kind of said we gauge U. But what we actually do is we only gauge this correction C. And like here, near space-like infinity, we have these coordinates Y. And so this omega-1 gauge that we had would be just the span of dy1, dy2, dy3. So here we then require that there's no dy0 component. And then one also has to choose equations, so to really get a square system, which is then symmetric hyperbolic. Now, in order to analyze this symmetric hyperbolic system as a PDE, we write it down in standard matrix vector form, which I did in this last item. Now, it is very important that one does this using a homogeneous basis. And also note that here I have some function s, and this is 2y0 plus norm of vector y. So you see that we differentiate with respect to a homogeneous derivative again. Now, this system is symmetric hyperbolic, so in particular, this matrix in front of the principal term is symmetric in I and J. And further, it has the usual positivity properties. Now, let me indicate where these terms come from in this PD. We have the terms that are linear in C and independent of V. These come from the Minkowski background. The bracket of V with C gives a principal term which depends on V, and then two types of linear terms which don't differentiate the C. This quadratic term gives the quasi-linearity, and then there's also a bilinear term in C which does not take derivatives. And then there's the inhomogeneity. Now let's look a bit, or let's look at the coefficients. So the A's, the L's, the B, and the F. Because we are working with a formulation of the Einstein equations which is regular at null infinity, so in particular the D and the bracket are smooth differential operators, including at null infinity, these coefficients here are smooth at null infinity. So on the closure of delta, not spacelike infinity. So each of these matrices, they're smooth at null infinity. And because we are using a homogeneous basis and we take derivatives with respect to homogeneous vector fields, these coefficient functions are also homogeneous of degree 0. So they are invariant under scaling y by a positive number. Now, therefore, the only terms in this PD which are leading order with respect to homogeneity are the green ones, namely the ones that come from the Minkowski differential. Namely, these terms are O of 1, whilst the other terms, which involve a V, are O of y times log y. So we see that the terms that involve a V, and hence, like these are the terms that involve Kerr, these are lower order in terms of homogeneity. And now by using this observation, one can then construct the solution C using a priori estimates for C and its derivatives. Actually, in order to be able to exploit the homogeneities and the energy estimates, it is one wants to use energies defined over these types of level sets, which are actually precisely the level sets of this function here. So that's all I planned to say. Sorry, I didn't realize that time went so fast. So yeah.
Thank you.